Okay. That's amazing, huh? All right. Sorry about that. I was trying to make sure everything's working, huh? So, I'm Jerry Buxton, Vice President Engineering for AMSAT here in Fox Labs, which is my workshop in Granbury. And I've got RadFxSat here, also known as Fox-1B internally to us, and probably by some of you out there. I thought that since I have it now, we haven't started the testing on it that we're going to be doing in a few days, or hopefully tomorrow, I would give a little tour of it, because in the presentations that I do, say at Symposium or at Dayton and Hamfests, 20-25 minutes to talk isn't a lot of time, and it's really hard to get a lot of meaningful information into it. Now, in this case, not too many people have seen an actual flight unit, and some of you may have seen what I call the full-scale model, which is a mock-up that we have that is built from the actual space frame and circuit board blanks, and we put some lead inside of it to simulate the weight of about 1.3 kilograms. That's probably about the closest that you've come. You've seen some videos with the engineering model and such like that, but I thought what I'd do is kind of just give a little talk about RadFxSat and how it's put together, what it looks like as we get ready to put it into space. So currently RadFxSat is sitting here and she's charging. You see that that is done through a simple USB connector. We call that the umbilical. The USB connector is connected to this breakout box, personally designed and built by me. And I can't do much of what's going on in satellite, but I can do something this size pretty well. It's got an on-off switch that we connect it to power so that we can charge the battery. It's also got a USB output that goes to the PC so that we can talk to the IHU internally there through the diagnostics. And it's got a place to plug the voltmeter in that actually measures the voltage of the battery as we're charging or any other time in between. Currently at 4.132 volts, so I charge it up above 4 volts before we do our testing so that we know we're in a good range and that it will last some time. We don't run the battery down during the tests. So I'm going to shut that off. For your information, how is it charged? We've got this charger over here, and I think you can see it. It's a simple USB charger I picked up from Radio Shack. Puts out about 5.1 volts. And that, as I said, is switched through the umbilical battery tender, connected directly into the satellite. We have a couple of diodes in series that are used to drop the voltage from the 5.1 to 4.3, 4.3, 4.35, which is the voltage that the batteries like to see. So it's really a pretty simple operation as far as charging it goes. And you can take it practically anywhere, plug it in the wall, plug it in the satellite, and there you go. So I will shut off the tender and the voltmeter, disconnect the umbilical, and we'll have a look at RadFxSat, which in the flight mode isn't real easy to pick up because you don't want to touch the solar panels at all, so you got to get the edges and corners just right. Notice I'm wearing an anti-static wrist strap and good old nitrile gloves. You're looking at the plus X side of the satellite right now. As you can see, it's pretty small. I think that's something that's kind of hard to wrap your head around, but this is the actual flight unit. Speaking of wrap your head around it, it's smaller than my head. Of course, that can be pretty big sometimes. The dimensions are 10 centimeters roughly per side. So it's a 10 centimeter cube, approximately 4-inch cube. And we've got solar cells on all 6 sides of it. This is plus Z you're looking at right now. This is minus Y, minus Z, and so forth all around. So that when it's in orbit, it's always an opportunity for one side of it to be pointing toward where there's going to be some sun. Let me mute the PC here for a second. Okay, so like I said, kind of a tour. Right now it's in what we would call the launch configuration. With the launch configuration, the antennas are stowed, and if I put it up here closer to the camera, hopefully that's a good shot. You can see that this is the minus Y side. The minus Y side is the side which has the transmit antenna. The transmit antenna is approximately 20 inches long, and you see that it's coiled around. Thought I muted that. Anyway, thanks for the retweets, guys. Hang on. There we go. It's a good thing I build satellites and don't operate PCs, huh? So, the transmit antenna, the 2-meter antenna, the root of the antenna is connected to the PCP right down here where my finger is. It's stapled and soldered to the PCB. Then the antenna coils around in a counterclockwise or anti-clockwise for those of you across the Atlantic for about 2 turns, and you see the tip of the antenna right down here. The tip of the antenna has a little loop in it to which we tie some fishing line. The fishing line then carefully runs under this standoff insulator and around the little resistor here. It's a 6.9 ohm resistor, 6.99. It makes one loop around that, and then it's tied off again to this standoff insulator. So the idea for deploy is that once the satellite has run its countdown, when it's ejected from the P-pod, it's not allowed to transmit or deploy any antennas for 45 minutes. So the IHU is actually running in a low power state, counting down. We go 52 minutes or so in order to be safe, that we don't want to be real close to that 45-minute margin, otherwise it might spook the launch provider. So, you know, it's taken months or years to get there, so what's another 5 minutes, right? When the time comes, we apply the direct battery voltage to this resistor, and the current runs about 1.5 amps, depending on the voltage. That resistor gets pretty hot pretty quick, melts right through the fishing line. And as soon as it does, that lets go of the antenna. The antenna is made of nitinol wire, so it's going to want to spring back to its original shape, which was straight, and it will extend itself right down toward the camera here now from the minus Z side of the satellite. You'll note that the way the antenna is coiled up, we have an insulator here, here, and here, but we have a conductive standoff up at the top there. The conductive standoff is there in order for us to know that the antenna is stowed. When the antenna is shorted, or touching that, it causes a short to ground. The IHU sees that as an indication that the antenna is stowed. So similarly, we go flip around here to the plus Z side, and you can see the receive antenna. The receive antenna is only about 6 inches long, so it makes about a half a turn from its root, which is up at the top in your view, down to the sensor indicator. And then, once again, the fishing line. This one makes a little extra trip because of the proximity of the tip to the standoff. It makes a little trip up around the side and then back around the resistor and such, as you can see there. And the same thing happens. We actually deploy the transmit antenna first, so that if all else fails after that point, we can at least get telemetry, hopefully, from the satellite and see what happened. So about 10 seconds after the transmit antenna deploys, the receive antenna will deploy once again after it's been ejected from the P-pod, and it extends out the plus Z side of the satellite. Some of the things that makes me think of something that I think I caught in an email today or something. You know, first of all, the polarity of the satellite, like with you're using your arrow antenna or whatever. As you can kind of see, the transmit down out the minus Z and the receive out the plus Z. They're linear with each other. Each of them actually forms a dipole. The 2 meter forms a dipole between itself, the body of the satellite, and the 70 centimeter antenna. And the 70 centimeter antenna forms a dipole from the whip itself and the body of the satellite. So they are in the same plane. There's no, of course, vertical or horizontal in space, but whatever way you have your receive antenna oriented for the best signal, likely your transmit's going to look for the same thing. And you do notice sometimes that there can be some fading, and that has to do with perhaps the way you're looking at the satellite. It's magnetically stabilized. There's a magnet in one of the sides here to keep the plus Z generally pointed toward the north magnetic pole. So from where I am, kind of like this. The closer it gets to the North Pole, the more it tends to point down toward it a little bit there. But depending on where you are in that orientation, you may be behind the satellite in a sense from the receive antenna or the transmit antenna. Okay, looking at the plus X side here, this is what we call the remove before flight pin, this little pin with a loop of cord on it. That's the pin that safes the entire satellite, keeps everything shut off. Again, in our launch configuration here, that remains in the satellite until it's inserted in the P-pod, at which point it's pulled out. That keeps everything cut off so that while we're working with it, while the launch provider is integrating it, they don't have to worry about anything accidentally turning off. In conjunction with that, and I'm going to flip it over here, on the minus Z side, we have in your upper right and lower left 2 springs. These little springs, which, there we go, are compressed when the satellite's in the P-pod, either stacked on another CubeSat or on the bottom plate of the P-pod. What these do is provide a little extra push once it's released from the P-pod to help the CubeSats separate from each other as they deploy. So there's one of those in each opposite corner. And then in your upper left corner, lower right corner, you might see a couple little black posts. Those are Delrin. They are simply a plunger that pushes against what's known as the deploy switch. The deploy switch is the second mechanism that prevents the satellite from turning on. When the satellite is integrated into the P-pod, both deploy switches are depressed, again because it's up against another CubeSat or on the base plate of the P-pod. These also shut off all power to the satellite. So at that point, the remove before flight can be removed, and these deploy switches are now keeping the satellite off until the P-pod door opens, the satellites are deployed, the switches open up, and that's when everything fun starts to happen. So this is the whole package, as I said, in our pre-flight configuration. We will take this and we will test it in this configuration. Then we have to do later in the next day or two what is known as a day in the life test. A day in the life test is required by the launch provider. It is not actually a test of the satellite itself. Functionally, what they're wanting to look at is to make sure that these antennas don't deploy and the transmitter doesn't come on before that 45-minute mark. So we'll take it, lay it on the bench here. That'll be on live video as well, as was a previous test we did. But we have to do it again because we had to make a change to the satellite. So we have to recertify that. At that point, you'll be able to see the antennas deploy because we'll pull the RBF pin, time how long it takes for it, and then actually, once we've achieved the 45 minutes, we know that we satisfy the launch provider and they're actually happy, but we let it burn the whole 50 couple minutes until the antennas deploy so that we're satisfied that our deployment mechanism is working our way as well, and our software. So what's in RadFxSat? Well, we've got the engineering model here. And some of you may have seen one of these at Dayton or at Symposium. I've taken them along for show. This engineering model has all of the live circuit boards in it. You can see in the top here are the 4 Vanderbilt University ISD radiation experiment boards. Then below that is our battery board. You can see the A cells on there. Those are NiCad cells. We choose NiCad because they have a long history of several thousand discharge and charge cycles. They have this kind of bronze looking stuff around them is actually a heater. It's a little elements wrapped around it so that we can heat the batteries if they become too cold out there in space. You can see, because you need to have 0C or higher to charge the NiCads, otherwise you're going to harm them. Running right down this minus Y side, you'll see the bus connectors. That's how all the boards fit together. They're 60 pins, so they pass all these signals and power and such back and forth between all of the boards. Theoretically, we could take the boards and rearrange them in any order, although some of the other logistics like the batteries for center of gravity and stuff pretty much dictate where they are right now. But it does make them easy to swap out, basically. Below the battery board is the power supply. This is one of our new MPPT, Maximum Power Point Tracker. You can see a little connector on the edge here. That is where, and I don't have one handy, but the solar panel, when it is attached, it has a connector on the inside, an MEC connector by Samtec, that fits right over those pins, and that's how the solar panel makes contact with the bus of the satellite to provide the solar power, temperature, and also for the antenna deploys. There are extra connections there for the antenna sensor and antenna deploy. Below that is our IHU. The IHU stands for Internal Housekeeping Unit, and what it is the MCU, the brains of the thing, as people like to say. That is the computer that runs the satellite. The IHU also has mounted on it, because of the available room, the MEMS gyro experiment, the one that was produced by Penn State Erie, that measures the X, Y, and Z rotation of the satellite. And you can see that in Fox-to-LEM from AO85. That's one of the readings under the solar panels. That experiment was designed to fly up in the experiment bay originally, but because the students didn't finish it because they graduated, they didn't finish the flight unit. When it came time to build the flight unit, Tony determined that we had room on the IHU, so we went ahead and put them there. Therefore, they wind up flying on actually all of our Fox missions rather than just Fox-1 or Fox-1A as was intended. Below that, you can see a little bit of shielding. This is the receive board. And right below that, you got a little corner of some shielding as well. The transmit board is on the bottom. Transmit coax comes out, and actually this would loop around and connect to the solar panel, but I have it loop out the side so I can connect a dummy load to it. And similarly, the receive antenna coax, it runs up the side and loops around the top to connect to the plus Y solar panel. I can't think of much more else to say about that. It is, this engineering model has been used, the batteries have existed since Fox-1A, so that's kind of a good testament as well to the hardiness of the NiCad, because I've had this for 2.5 years, and it's been charged, discharged, and otherwise mistreated, and the batteries are still doing a fine job. So I use the same batteries. The IHU is a recycle from the Fox-1A spare, but it can be loaded with the new software. Of course, the MPPTs of the new brand, and the transmitter and receiver actually the Fox-1A spare as well. So they're on the same frequencies as Fox-1A, which makes testing with the engineering model interesting, because if I want to copy Fox-1A or work it in my shack, I have to make sure this is off, otherwise this is what I hear. So starting up hopefully tomorrow, at least for sure Monday, what we're going to do is we'll do some tests. First we do some tests on Fox or RadFxSat that are designed to look at it in this launch configuration. In other words, in the P-pod in a sense. Is everything shut off? Does the IHU operate through the umbilical and diagnostic mode? Or do the antennas show stowed? Do they not deploy when you pull the RBF pin and such like that? Then the next phase of testing will move into that day in the life test. The day in the life test is 5 minutes of action followed by 50 minutes of waiting, followed by about 4 minutes of action, and then that's over. But it's fun. You get to watch the antennas deploy and such. Once we get the antennas deployed, we'll do some other tests that we call, the startup tests. In other words, we'll make sure we'll take it in that configuration, make sure it starts up, that the transmitter sends a beacon and such like that. We don't want to do those tests with the antennas stowed, of course, because they are in fact grounded in order to sense that they are stowed. However, the PA designed by Mark Franco, N2UO I believe is his call, is designed to be able to take that just fine. And actually, we do some tests just prior to launch with them stowed, and we are transmitting with the antenna in that configuration, and it has held up very well. So that's a very good design. RadFxSat is essentially the same bus that was used on Fox-1A, Fox-1 Cliff, Fox-1D. The only thing that changes is the experiments. These 4 bays at the top, we can put whatever university experiment or experiments in them that we like. In case of Fox-1 Cliff, Fox-1D, Fox-1 Cliff has 2 Vanderbilt experiments, which are the spares from Fox-1A, and it has the Virginia Tech camera experiment, which will take JPEG pictures. Fox-1D has the University of Iowa Herky experiment, which takes up the bottom 2 slots, and the again, a Virginia Tech JPEG camera experiment. And RadFxSat is totally Vanderbilt University. That's about all I can think of to share with you right now. I hope that gives you a little insight into what the satellite looks like, what it is. Like I said, this is the flight model, so if I drop it, you'll never see me again. But I hope you enjoyed that. Leave a little message or something on YouTube there, or Facebook, or tweet or something. Let me know if you like that stuff. I'd like to do some more of it, because like I said, it doesn't always seem to be much time to share at the big gatherings, and a lot of you can't always make those anyway. So 7-3 for now.